So in this panel, we have seen a good presentation of different technologies, different implementations, different strategies. So from gate-based to quantum annealing, and we have also been talking about Nitrogen Vacancy Center on diamonds, like quantum brilliance and so on. It looks like there's quite a big range of technologies and implementations, different range of way to interact with the quantum environment, okay? But quantum computers are not vastly available, okay? So this points to the emulator type of thing, to get people upskilled and ready for interacting with a system. So what do you see the challenges currently, assuming this kind of a scenario that we see now in getting people ready, getting the knowledge, getting certifications that we have seen from Qiskit, from some of the others, and how do you see the readiness in the community from point of view?
Maybe the main challenge right now is the talent. So we didn't have a lot deterministic different profiles. So we need architects and engineers and physics, mathematics. So in the university in Spain, Spain has different masters and PhD programs. So I think it is important focus in the talent, because I speak with I speak with you, and in Spain, we have a good talent. So in Spain, don't have the inversion in research. So maybe I think this is we focus in this topic.
If I follow up, I would say that, is it working? No. Okay, so let me do a follow up. I mean, for sure, talent. I mean, talent in any of the topics. I would say that it's new technology. There's also a scarcity of talent. That's for sure. And quantum, you can imagine, right? The physicists are the ones, and you are focusing on one specific technology. It's even harder. And as you were mentioning, there's several technologies already here being exposed, but in the quantum, there's even more. And we don't know which one and for what purpose is going to focus. So we are still in this deep depth exploratory phase, let's say. But in terms of for us, the big challenge is to lower the hype. So it's like we need, for sure, quantum when it's gonna be ready, it's gonna evolve and provide a lot of value. That's for sure. In the precision, in cost efficiency, in providing actually value for the end user. That's for sure. But right now, what we need is, and this is a challenge, is how we can say that, because it is a deep tech technology, how we say that it's going to provide value. And that's why quantum emulators is also like a good opportunity to say, okay, let's educate people, because it's not easy, this transition, and we need to explain to all communities, to all clients, all different industries, that there's going to be value, but now we need to raise, because otherwise there's a lack of a mismatch in terms of expectations. Because when you are working with them in POCs, then you say, but what is the value, right? You're not running into a quantum. These 1,000 qubits, like, no, wait. So there's a process of being that. So this is a major challenge that we are dealing, but we are moving. That's for sure. But yeah, I would say that. I mean, I have many other things, but I'll let the others to explain. Yeah.
working, right? I would say that challenge is what we have most in general. We are overwhelming with challenge. Yeah, talent for sure. And in talent, I don't know if you feel the same, but I see a lot of potential quantum algorithms developers. There's plenty of them from the masters. I don't think we have enough space for them right now, probably in the future. But adapting the classical to the quantum, communication between the quantum. It's like when machine learning started. Everyone wants to be machine learning, but we need also data engineers, we need systems engineers, we need a lot of different profiles to be prepared. And I agree also with there's the challenge of the hype, reality, and hate. So yeah, it's people that thinks that quantum is going to solve everything. Then we have the reality. That means that we have to solve all these challenges of compilation, transpilation, communication, how to parallelize the different loads. There is a plenty of things to do in the meanwhile, and then also the haters that thinks that there is no future here. Yeah, for sure. And between those, we can put all the challenge together. So technology is a challenge. And to decide which is going to be the correct technology, I don't know. This is like beta and VHS. Maybe there is one which is better, but there is some commercial guru that makes another. So let's say that the challenge is that we are on moving suns. Right now we have to work carefully, do strong steps, mostly for Europe and for the different companies. You can mistake yourself, but it's important that you do good steps, working on MVPs, but also trying to define as much as we can. So I would say that's a little more what I'm saying.
So then talking about the quantum hype and the quantum hate, there was something interesting that IBM and also PennyLane make a very big effort to make an entry level of quantum computing very easy. So one can do pipe install, PennyLane pipe install, Kivo pipe install, Qiskit, and get a bunch of notebooks explaining step by step what the algorithm is doing. So if someone wants to be involved in quantum, they have tools to be involved in quantum. So, and we suppose that this is a way to decrease a little bit the hype and the hate, because we're decreasing the hype because people is running algorithms in real quantum computers or in their own laptop or in an HPC. But there is some point that people say they can think maybe, okay, I'm running in 5 qubits and I get these probabilities that are a little bit out. What we should do, they can fit a little bit the hate. But I think that the effort that has been done by the community, by hackathons, the dissemination talks, all this stuff can help a little bit to decrease the hype and the hate, and also to commit to physicists, mathematicians, computer engineers, to don't be afraid of the quantum level. Because when you go to a quantum course, the first thing that you have is all the equations, all the Pauli matrices, all the operation. I say, whoa, I want to run away. But we are lucky that there are a lot of community effort to make it an entry level.
Yeah. I would say that when we start the computation, the classical computation, there was a clear necessity. I remember, maybe I'm wrong, but it started with the tellers, with the punched cars in the States for counting the population. They spent like 10, 15 years for counting the population of 1 year. So there was real necessity, and there was a lot of investment in the right direction at that time. Yeah, a lot of investment. Right now we have investment. We have a lot of investment on the European flagship, but I would say there is not the necessity. There is like I wouldn't say the curiosity. There is if I have a use case, I will spend. But at the very beginning, there was an spending as a must. This is one of the challenges I'm facing as well.
So I have a question. I want to talk a bit more about the challenge of the talent, right? So we've seen today several presentations that you have explained that the simulation has its limits in terms of how many qubits you can simulate. And do you see this really as a challenge, as a barrier for the entry level? So we've seen in classical computing, experimentation is key in order to develop new algorithms and scale up, right? So, and it's very easy. I can open Jupyter on my laptop and start playing, and then I can add more data and scale up to supercomputers or whatever. Do you see this limitation in the number of qubits that you can simulate hindering the development of new algorithms or the involvement of newbies on the quantum world?
I would say not for the newbies, because we have plenty of access for them, but the number of qubits, so you can access easily to the technology, but the number of qubits, the limitation of the number of qubits, it's a challenge, and it's a limitation itself for several products. So the case I explained before, it's for financial simulators. You have cases where you know that quantum is going to give you advantage at some levels, but you cannot use it because it needs 1 million of qubits. So yeah, I would say it's a limitation, but I wouldn't say it's for the newbies. Maybe for the motivation of the newbies that see a long way to get to the result. Long way, we're talking 2 years, 10 years, 20 years, depending on the scale you want to achieve. But yeah, the challenge for me is the number of qubits more than the access itself, and maybe the motivation for the newers.
Yeah, let me add also, you were touching into the talent, but for an entry point, I wouldn't see right now as a challenge, because that even for quantum experts in terms of algorithms, so they are already focusing on how we can encode the problems, and we can split the problems in using the technology that we have right now, and just solving that is also thinking about, okay, the ideal scenario will be 1 million qubits, but okay, what happens if in 5 years we have like small QPUs that the encoding that I already prepared, then I can start using that. So and again, it's I would say that for the industry, it's a long process to move the business use cases, their business processes into using quantum, and then starting to reformulate their current algorithms, their current applications, thinking about quantum solutions. I would say that this is not going to happen overnight. So if we show that with the small QPUs can already prove some benefits, I would say not quantum advantage, that's for sure, but this is gonna help like as an entry point, and emulators is a way to do so as well. That's for sure. So this is something, and using kind of an HPC centers, using tensor networks. I mean, we can go into high numbers also. Like there's also like research going on that area, and I would say that helps also on using that. So I wouldn't say that right now the limitation is in the number of qubits. I mean, that's for sure. If you have a powerful computer, that's for sure. But I would say that this is kind of the easy path. Okay, let's explore how we can do that, and also just touching into the talent. And actually, you were saying, because there's many like quantum software quantum application experts, and actually there are many of them. And most of, I would say that the industry and the talent is going more towards of the education, is going more towards that part. But we need also people into the hardware side, so people that knows how to deal with quantum hardware, but also control engineers. So it's not always about quantum. It's how would you encode, because again, it's like the beginning of the computer, right? So it's kind of more a control engineers rather than, and then it's gonna be the software. But right now is more kind of a theories area, which there's many challenges there as well. But in the hardware side, that's for sure. There's a scarcity of talent in Europe, but totally. I mean, that's for sure.
If I can add just one thing, we have to think that the journey is going to be funny as well. So all the way off until when we achieve, or maybe we not, maybe the haters are right, and we want to achieve the quantum abundance. We don't know, honestly, we don't know right now. We are believers that we will get that.
Otherwise, we won't be.
Yeah, absolutely. But even if it doesn't happen, the journey is funny. I mean, we already got the quantum communication, the QKD protocol. We got optimizations, even if only with simulator qubits. There is plenty of things to discover in that journey that has been already discovered, and we will discover quantum sensors, for example. The journey is so funny and so exciting.
We don't forget about you, William. So if you want to join the discussion, just raise your voice.
Sure, thanks. I think I'd like to just echo on some of the points that the other panelists made. When it comes to scarcity of talent and when it comes to some of the challenges, that we see. Really, I think one of the main barriers right now inhibiting greater adoption and greater people entering the space is this consistency of user experience. So for example, if many students, whether it's at the undergraduate level or at the PhD level, are learning to interact with quantum devices in an academic setting through traditional HPC clusters, this is going to be very different than if they are then transitioning into industry and accessing these devices over the cloud. And so to the extent that we can provide greater emphasis on user experience, make it easy to understand, easy to interact with, I think that will unlock the ability for a greater degree of people to start playing with these devices. Because it's true, we're not in an age yet where we have meaningful quantum advantage, but we are in this really interesting exploratory educational phase. And so it's very important to bring as many people as possible into that conversation.
Okay. So we have been discussing about different mechanisms to interact with regular HPC clusters. Some of you already mentioned limitations in the way to interact with the quantum computer over a network. Ethernet, InfiniBand has been mentioned, problems with I/O, and so on. Some of the vendors, they do have kind of a coprocessor that can be connected directly to the PCI Express and so on. So the open question to all the panelists today is, how do you see this interaction between quantum and HPC in the future, in the near future?
Well, in the near future, I don't know, should be maybe as nowadays, connecting to a cloud, getting the data from there. But the thing is, this can be a little bit, so let's start at the beginning. I imagine that the future will be of HPC and quantum is use quantum as accelerators in the same way that we use GPUs. So my dream is receive a box, say to my operation teams, go there to that company and install this piece in the cluster and has PCI Express connection to the GPU and the QPU. It will happen. I don't know. There are some companies that have some mockups for 2025, something like this, that is connected directly to a PCI Express. It will lead to have some algorithms that can interact in the same way that we interacted to GPU. So try to imagine that we are doing an operation that I want this piece of the code running CPUs, another one running in GPUs. If we have that connected to the cloud, the overhead is quite big. If we have that connected to in a local network via Ethernet, Gigabit, or InfiniBand, that would be great. But if we have directly connected to a PCI Express, that would be perfect.
Maybe it's very interesting the question. So I think in the future this is possible because in evidence the proposal we present this week is just the first step for this architecture, because we have a quantum simulator in appliance and memory and hardware and software in your own appliance, but right now it is possible only acquire the software and complemented the HPC. So in this year will be possible combine HPC quantum simulator. Maybe this is the first step for the combine all quantum technology and classical technology.
Yeah, as a follow-up, so there's this Euro HPC initiative, right? That is gonna take place in the few next years, and the idea is to connect 6 HPC centers within Europe, and for each of these HPC centers, the idea is that they're gonna have a quantum computer in their facilities, and then it's gonna be a different type of technology in terms of quantum. The idea behind that is that the HPC centers also need to learn about how to use the quantum computers, how to use different type of quantum computers. And then the beauty of the project, I would say, that is also like the idea to interconnect all 6. So then a user, and this is the user perspective that is crucial, that whenever I want to run an algorithm, I shouldn't be as agnostic as possible about what is behind that, right? And so that if we kind of work in this same UI, the user interface, I would say that it's going to also move very much aligned in not only on the technology side, which is for sure a challenge, but also in the user experience, so that I connect and only with this as a kind of a experience to understand how users can connect only of these 6, and then I want to run something, and maybe if I'm possible through the cloud, and then say, oh, I have these 6 available, I want to run to all of 6. Let's see, I can do a benchmark, and then I understand how, for my use case, it's better to use this technology rather than the other one. Just understanding and learning about that, I would say that would solve a lot in terms of communication, then to how that process is going to be smooth in the future. So yeah, we are in the learning process, always learning. Yeah, and have fun, as you said.
Yes,
have fun.
I would say exactly the same. We are in the learning process. It's plenty of challenge, and I really like the simile with the GPU. But for example, if you have your GPUs in Japan and your CPUs here, it's a good setup. So it's the PC, you know, how you can avoid that. Even if we have the best communication, we have challenge on the compiling, transpiling, because you can feed the GPU is very few used. Mostly is the pre-processing, and the pre-processing, optimizing the circuit, compiling the circuit. And yes, this concept we are following, we are looking for this concept of serverless. So the scientific just send a job and doesn't care if it's GPU, QPU, he's just got the bare result. But for getting that bare result, you need to check the delays, you need to check how to join the outcomes. And for that, we are learning in this funny way or path. Yeah, we are learning.
William?
Yeah, just to follow up on that, I do see, we do kind of have 2 diverging models here, where one of them is with the quantum computer physically co-located with HPC, classical HPC resources, but I don't see the cloud model going away anytime soon, where you're going to have a quantum computer very, very far away from your classical resources. I think perhaps we should think of these really as two separate models with two entirely different sets of algorithms that are suitable for them. When it comes to the devices being co-located, things like some of the work done by groups like Quantum Brilliance, where they're able to actually install something in a rack server, hook it up with higher speed interconnects, even though the quantum hardware still needs to progress a little bit. I think this is sort of the beginning of something really interesting where we can then start to actually work on interconnects. But again, I don't think that this is going to be the limitation or really the bottleneck for quite some time to come.
Yeah, just to add an example. Last year we deployed runtime. Runtime just means that you send the whole program instead of computing in your laptop or your HPC, whatever, and send to the cloud and then getting back the results of the quantum and co-process everything. You send the whole program to a very limited hardware we have there close to the quantum, and we compute the classical very near to the quantum, and then we interact depending on the load, but the minimum is 4x. The minimum is 4x. If you are talking about VQEs, it can be even much more. So yeah, it has to be co-located, and you have to prove that just co-locating you are improving for at least the performance.
Any more questions? Yep.
Okay, as my small knowledge about the topic, there are many different platforms with different characteristics, like the time that you have in the stable state and the doors that you can use depends on the technology. These kind of things, from my point of view, is a drawback to start in the quantum computing, because you need to bet for one platform at the end. Do you think that it's possible to have some kind of open layer that abstract all the stuff and work with all the technologies without many knowledge about that you have in the hardware, like we have now in the different binary PCs or something like that? Because really, I think I'm waiting to collapse in one technology, the quantum computing.
I would say it won't collapse in one technology. We have Intel, we have AMD. If you compile in one side, you cannot go to the other, but you have schedulers that can compile in both and use both. I would say it's the same, more or less the same. We cannot define right now which is going to be the best.
Yeah, but I compare more like GPU technology. Okay, now NVIDIA, if you need to bet, is you need to develop something, you develop for NVIDIA, because it's who probably have the better software stack and something like that. It's clear in this case, but in quantum computing nowadays, it's not clear where you're going to bet, where you make your effort of your code and develop really your code, and where you go in the future with your code, because probably if this platform disappear, you lost all your work.
Yeah, I would say so. For as usually with new technologies, what it needs to happen that the industry works into standards. So standardization is the way to go in order to avoid what you were saying, right? So if you are looking for a specific vendor and that vendor is not the winning technology, or just you cannot run anymore your algorithm, then you cannot run it there. So and I would say that what happens is two things, right? First, the technology is not mature enough, and we are still exploring that. We are a few years away in order to understand what are the benefits of each technology. Maybe, as you were saying, Intel and AMD, maybe there will be complementary technologies for specific use cases. We don't know, and maybe for one you can run all of them, but then if you want to be super specific, it's better that way, right? So it's and here and it is a good one. Like Intel AMD is like a specific chip technology, but here we are talking about quantum computers. So there's many layers as well. So there's also like a software layer. So and the idea is like. There's advances in different layers, and emulators, for instance, is helping in order to evolve the software stack, for instance, and in order to be also started conversations in terms of standardization on that layer. So there's work on different layers, and I would say that standardization is the way to go. But it's gonna take time. So yeah, I mean your question is pertinent in the sense that yeah, we need to find that place, and we're aware of that, I would say. And what we need to provide is value for the user, so that the technology is also in terms of quantum computing, right? This black box is as agnostic as possible. So you encode something into this one, but then the definition of your algorithm can be described into, let's say, a descriptive language that then it can be run into several backends. So yeah, that's a challenge also. You were talking about challenge before, so this is also a challenge to be.
I would say that talking about funding, we could spend hours discussing if the NVIDIA is a good signal or not, for example, because we are in MVPs. We are in MVPs and we don't know. You don't know if it's better a general purpose or it's an accelerated. We cannot define depending on the workload. And depending also on the application, and you have to compile everything, or even RISC or FISC, or even the number of registers we have in a processor. You prefer the bigger, but for network, for example, or for cloud edge, everything would have a different, for example, if you need quantum computer based on superconducting, but that needs a super freeze temperature, maybe it's not used in the future for the quantum processors that can use on the edge devices. And maybe the quantum brilliance, the diamond technology is good enough for that case, but they cannot grow to thousands of qubits, not nowadays. It's plenty of different alternatives. I wouldn't bet. Well, you can bet on a joint venture between Everybet, Kilimanjaro, and IBM. That will work for sure.
Okay, I have been told that the lunch is ready. I would like to thank you again, all the panelists, for your contribution. Thank you so much for joining us. Thank you so much, Will, for joining us at this time of the day. We really appreciate that. Or night, yes.
Thanks, guys. It's been great.
Thank you so much.
Thank you.